We've come to the point in our evaluation of the overall process of water main installation where we need to look at the actual installation of the pipeline material itself. Before doing that, before diving into those details, we'll remind ourselves of what has been relatively constant theme in that the care that we take in both the installation as well as for the material itself, as we've said before, plays a large role in the success of the project, in the overall length of the expected useful life of our pipeline installation. So we're talking about taking care of the material. Once again, we're talking about keeping it clean during the process of installation to minimize problems with leaks, to minimize the amount of flushing or bacteriological problems we might have. So taking care of the pipe, keeping it plugged or covered at the end of each day as we're continuing through the process of installing pipe to keep critters and such out of it, to make sure we don't have bacteriological problems. All of those are the things that we need to continue to keep in mind even during the course of the actual installation of the pipeline material itself. So as we move into the world of pipeline installation, let's familiarize ourselves with some of the terms associated with pipeline and trenching. So we see a trench, we know the ground surface up at the top. We'll show our pipeline in our trench. To begin with, the bottom of the pipe is referred to as the invert. Actually, it's the inside bottom. It's the flow line of the pipe. But many plans will identify the pipeline invert. We will use that term when we get into the math to identify the elevation, at least, of the bottom of the pipe. The material placed in the trench on which the pipe lays is called the bedding. It literally provides a bed on which to lay pipe. And it's important because we need to use the bedding to make sure that we have a stable support for the entire pipe. We'll talk about that in a little more detail here shortly. The center line of the pipe is officially known as the spring line. You'll see some plans that might identify that spring line elevation. The backfill over the top of the pipe is referred to as shading. You'll also see in some places it referred to as cover. The area around the pipe, the backfill compaction of that material is critically important to the overall stability of the pipe. And so usually you'll have some sort of material around the pipe, oftentimes sand, that is easy to compact and can provide uniform support for the pipe. The technical term for the compaction of the material, again often sand, from the bottom of the pipe up to the spring line is called haunching. And it gets specific attention because effective compaction of that area provides the majority of the support for the pipeline. So as we look at our trench and our pipeline installation and kind of revisit some of those terms. Again, if you look at the bottom of this exhibit, you see that the reference to the pipe invert elevation. Again, the elevation of the bottom of the pipe is the invert. What is referred to on this drawing as a pipe base is our bedding. The pipe zone is the area from the bottom of the pipe over to the top of our shading. In this case, this detail shows that shading is going to be 1 foot. That's not a universal requirement. That was the requirement for this particular project. It may vary a bit, but anywhere typically from 6 inches to 12 inches is pretty typical. So you have our bedding, we have a pipe zone. The next section up is the trench zone. That's the backfill of the trench itself over and above our pipe zone. The pipe zone compaction and backfill is really about protecting the pipe. The trench zone is more about protecting the street from future settlement. And then you have a asphalt section, including a subgrade and asphalt. So all of these are zones within our trench that we need to be familiar with. So let's go back to bedding. Again, bedding is simply the material on the bottom of the pipe, the material the pipe lays on. So it has to be suitable material. It has to be free of rocks and cobbles. It has to be free of debris. It has to be a material that can be relatively easily kind of spread out uniformly so that it can provide support for the pipe. Oftentimes that material is going to be sand. Very typical to use sand for bedding and for shading in a water pipeline. The picture on the right is a picture from one of the recent pictures from the Recycle Water Project that we are continuing to work on, and you can see the PVC pipe laying on a bed of sand. You will sometimes see crushed rock as bedding material, a little less common, but again, as long as it can provide that smooth surface, then it can work. The whole point is that our bedding needs to fully support the entire barrel of the pipe. We've talked about this a bit before. It's very important that you get uniform, full support for the entire length of the pipe in order to avoid future failures. You see kind of the exhibit on the bottom where it shows a void under a couple ends, and then you got a high point in your bedding. Well, with all of the surface loads, even the weight of the backfill, plus the loads from the street pushing down on the pipe, you're going to create stress right along the top of the pipe above where that high point is. And ultimately, that uneven support can lead to those beam breakages that we've talked about in the past. So it's important to completely support that pipe. And again, the material up over the top of the pipe between the bedding and that and compacting that material is what gives you really the full structural integrity of the pipe itself. As we said, the other important thing about the bedding is to keep rocks and any other kind of debris. And when we get into the backfill section, I'll show you a good example of the kind of nasty material that can come out of a trench that we don't necessarily put back in, but we make sure that our pipe bedding is suitable to provide that support for the pipeline. So we'll touch on pipe jointing. Clearly, pipe jointing is a critical part of pipeline installation. It's really about, and for a larger scale PVC project, it's about those bell and spigot joints. But as I mentioned when we started this discussion, keeping our pipe clean when we're putting it together is very important. If we get debris, leaves or anything else that might get in between our gasket and this point where the gasket needs to seal around the barrel of the pipe, then we're going to have leaks. We're going to have future problems. So keeping any kind of debris away from our gaskets is going to help with a successful project. In reality, the most common cause of joint failures is a failure to pay attention to keeping that clean. And even though the pipe may have been put together properly, even though the material is just fine, if we didn't keep it clean during the process of installation, we're likely to have leaks when we go to test it. Most common joint for long pipeline runs is going to be push-on joints. We've talked about those bell and spigot joints a bit before when we talked about the pipeline material. This picture shows a pretty good example with this cutaway. You see the beveled end of the spigot. You see the reference line that tells you that this pipe still has another couple inches to go before it's fully inserted, so that it's driven all the way home to make sure that we get that full embedment that's going to help to make sure that we get a effective installation without any leaks. This is the same picture we saw in the pipeline installation. It does a good job of, again, showing some of those same components. You see this beveled end. You see the gasket, which is what provides that seal. So in the event that we don't have some of these, for example, we cut pipe in the field, then we're going to have to use a saw or something to create that beveled end. And just as a reminder, the reason that we have this bevel is so that we can get the pipe past the gasket without doing any damage to it. So it creates a narrower end of the pipe that can slide through the gasket, and then the barrel of the pipe can make it through because we've lubricated it with some sort of food grade grease that will allow the pipe to be relatively easily put together. So a couple pictures of jointing pipe. You see the spigot end in the hand here. You can see the bell end down here. You can see that reference line on the pipe right behind where it's being held. So now the pipe's been inserted. The beveled end is kind of already into the beveled spigot end is already into the bell. You can see that reference line again. And then in this case, they're using a digging bar on the back end to push it home so that you get that full embedment and you get a good tight seal. When it comes to that discussion is really about installing joints of pipe one after another. But there are many cases where we need to tie in, as opposed to just running new pipe joint by joint, where we need to tie into an existing system. So there's a couple ways that we consider how we would connect to existing mains. The first is to literally take the pipe apart and install a T. That is a bit challenging because, of course, you have to take the pipe out of service. Anytime we're taking the pipe out of service, we introduce the potential for contamination. We have, of course, the issue with customer notification and inconvenience while it's out of service. And in reality, and sadly, one of the challenges in trying to do it this way is many of the existing valves in the system, depending on how old the system is, and the El Toro Water District system is less than 50 years old, we get a lot of valves that don't work. They'll close, but they don't seal tightly, and so we don't get a dry working condition if we're trying to cut into the pipe in some cases. So there are times where it makes perfect sense. This exhibit you see was one where we cut out the pipe, installed a brand new T to create that new branch. And that's a very effective way to do it if all the conditions are right. But there are alternatives. You've heard the term pressure tap, more commonly probably referred to as a hot tap, is the process of installing a new connection without taking the line out of service. So you see in the exhibit, you've got a valve that is connected to a sleeve attached to the existing pipe, and then you have a drilling machine that will cut a hole in the existing pipe, pull it back, and you have a new connection. Looking at this next kind of exhibit kind of shows the process. So you have a valve connected, you have a sleeve connected to the pipe, you have a valve connected to the sleeve, you have the drilling machine connected to your valve. The cutting end goes through the open valve, cuts a hole in the pipe. It will actually capture the material that it cut and pull it back out. And then once you pull the cutting end back across the valve, then you close the valve, and then you can disassemble your machine. So it is an effective way to create a new connection. We'll talk about it when we get to valves. There's nothing really special about the valve. There is something called a tapping valve that they make slightly differently to accommodate the cutter mechanism. But other than that, it's a pretty simple process and very common. It works very well. The only challenges you can have is what size. So for example, if the line that you're trying to connect to is an 8-inch and you want to cut an 8-inch connection in, that's a bit challenging because you're removing so much of the existing pipe. But with a fully, with a tapping sleeve that is a fully encapsulating sleeve that'll provide structural support given the portion of the pipe that's been removed, that may work. Typically, I try to avoid tapping size for size, like an 8 on an 8. We'll usually go up to 6 inches on an 8-inch line, up to 10 inches on a 12-inch line, etc. But I know there are many agencies that, because of the structural integrity of the tapping sleeve itself, are willing to do size for size taps. So we can take a look at some of the components. There's that fully encapsulating tapping sleeve I was talking about. So with that sleeve that goes all the way around the pipe, it's providing some structural support. So even though you're removing a portion of the wall of the existing pipe, the sleeve supports the pipe to provide the structural integrity for the portion that was removed. You have a tapping valve bolted up to the sleeve. And then this is a close-up view of the cutting end of your drilling machine. the drilling machine attached to the valve. So once again, it's going to, with the valve open, and the bolted assembly creates a seal. So you're not leaking any water once you make the cut. So the machine pushes the cutting head and cuts a hole in the existing pipe. Then it pulls back out and actually pulls the material that it cut out with it. That's called a coupon. And then you close the valve and you have a brand new connection. This is a close-up view of the cutter head and then the actual coupon that came out with it. The cutter head is made in a fashion that it'll hold on to that coupon and pull it back out with it. So that is our new connections. The next thing I want to touch on in pipeline installation is thrust restraint. So we've talked many times about the concept of pressure versus force. So as water's flowing through a pipeline, especially as you get to a joint, you have force associated with the pressure of the pipe that's pushing against the 90. And as you might imagine, that force would literally try to disconnect the 90, try to push the 90 right off of the pipe. Think about the numbers. In a 12-inch pipe at 100 psi, if you do that math, you're talking about over 11,000 pounds of force that's trying to pull that pipeline assembly apart. So we need to make sure that that doesn't happen. That's under normal kind of static, so to speak, conditions. Add in water hammer or surge pressure, and that 11,000 pounds could easily go to 20 to 30,000 pounds. So we got to pay real close attention at our bends, at many of our fittings, to making sure that the pipeline integrity remains intact despite all of the force acting upon it. So the potential, as we said, on the pipe assembly, you look at these exhibits, on a T, it's going to try and push the T right off of the pipe. On the 90, same type of thing. All that thrust is going to try and disassemble, is going to try and rip the 90 right off the ends of the pipe. Same on really any of these types of fittings. So we install what we call thrust blocks. And thrust blocks are simply a mass of concrete that will help keep everything in place. We will put them against what's called undisturbed soil, and so that's what you're seeing, for example, on the exhibit down here in the middle on the left. This mass of concrete is poured against the trench walls that were not disturbed, and part of the reason for that is it's very difficult to get back to 100% compaction. So we don't want our thrust block to move at all, because if it does, then the pipe can move. So by pouring it against undisturbed soil, then we typically mitigate the potential for our thrust block to move. Again, it needs to be a material that's not going to deteriorate. So you couldn't use like a wood 4x4 or something like that as a thrust block, because over time it's going to deteriorate, which is the reason that we use concrete. We'll center our mass of concrete on the location where the force is going to be acting, and that will help to keep the system intact regardless of the forces acting on it as a result of the pressure and change of direction associated with our fittings. This picture, again from the Recycled Water Project, we've got essentially a cross, valves going a couple different directions, so they've got what really amounts to thrust blocks on all four corners. This one is a slider bend, looks like a 22.5 degree fitting maybe, but with a thrust block, and you can see that it's poured against the undisturbed portion of the trench. In some cases, the thrust blocks are more challenging because there may not be undisturbed soil, or it's a vertical bend, or the ability to pour concrete up against a trench wall is some sort of challenge. So we then resort to what's called thrust anchors. In this case, we will pour a mass of concrete, and then we'll use an anchor that goes on this vertical bend over here. The anchor goes up and over the fitting and then is secured within that mass of concrete. So it does essentially the same thing, just a slightly different animal depending on the nature of the application itself. So that is the discussion of some of the topics specifically associated with pipeline installation. So now we've talked about excavation and digging a trench in our excavation and trench failure or trench safety modules. We've now talked about installing the pipe. So we will move from here Once we've installed our pipe, it's time to backfill our trench and kind of put the street back together.